Let's discuss the wonderful world of vectors. Very important concept, especially in Chapter 9. When we talk about a vector, we are talking about something very specific. We are talking about a quantity that has two things. The first of those things is direction, and the second of those things is, if I can spell it, distance. So if we give you a vector, convey that to you in some way, shape, or form, then you're going to know two things about that, or be able to find two things about that vector: which direction it is pointing in either 2 dimensions or 3 dimensions, or higher dimensions, theoretically, and the distance of that vector, which is going to tell you a lot about, well, whatever's going on, depending on what problem you're working on. So if I make this statement that I have a vector that is going from point A to point B, then I know, if I know where point A and point B are, the direction and distance of this vector. It's just going to be this vector right here that starts at A and ends at B. I wouldn't say a vector between A and B because I wouldn't know which way to go. So there's a vector that goes from point A to point B. Now what's nice about vectors is that I don't have to necessarily put it in that spot. I can put it anywhere as long as I have the same direction and distance. Then we call those equivalent vectors. Those are all the same vectors that I drew there, even though they're in different locations in what we consider to be R2 on this screen, I guess. But they're the same vectors, assuming that, give me a little bit of leeway here. There might be a little bit off on the distance, but assuming they're all the same direction and distance, that conveys the same two things. Therefore, they are equivalent vectors. Now, we will normally put them in certain spots, or we'll know where to put them, but again, we can write them in different ways. Now, since we have these vectors, we want to be able to do things with them. One of the things we want to be able to do is combine them with addition. And so we're going to look at combining vectors. Let's suppose I have a vector that looks like this. I'm going to call that u. And I have another vector that looks maybe like this, a little longer, straight down. I'm going to call that v. And what I want to do then is I want to find the vector u plus v. So it's very simple what we're going to do. We're going to simply start with u. I'm going to redraw u right here, and then at the end of u, so where the arrow is, at the tip of u, I'm going to start v. So I'm going to start v from there. So I'm going to just copy v straight down, start it at the end of u. Remember, I can put v wherever I want. And then the resultant vector is the one that starts at the beginning of u and ends at the end of v. So here, this orange vector is the vector u plus v. Now what's nice is that we could also, if I want, find things in the opposite direction. I could find the vector v plus u by starting with the vector v, going straight down, and then to the end of that tacking on the vector u. So here's a copy of u. And then what's v plus u? I start where v starts, I end where u ends, and you'll notice that we get the exact same vector, u plus, well, let's call it the way we found it here, v plus u. And so v plus u is equal to u plus v. That'll be true for all vectors. In other words, the way we mathematicians would say it is that vector addition is commutative. So that's nice to know. We like our addition operations to be commutative no matter what we are working with. And of course, if we do have addition, we'd like to have what we would call an additive identity. That's 0 when you're talking about the real numbers. It's going to be the 0 vector. And so we need to be very careful when we're writing to differentiate between the number 0 and the 0 vector. All my vectors, when I'm writing on the screen or writing in my notes, are going to have a little arrow over them to indicate that they are a vector. You should make a similar notation when you're writing your notes, working on your homework, any homework that you have to turn in. You want to make it very clear when you're differentiating between a vector and a number, or just a variable and a vector. So the vector 0, the 0 vector, it's the only vector that breaks the statement that I just made at the beginning of the lecture here, that every vector has magnitude and direction, because the 0 vector is a vector with magnitude, or distance, but the magnitude is 0, the number 0, so it has no length, but it does not have direction. So the 0 vector is the only vector that doesn't have a direction. Alright, and while I'm thinking about it, let me go ahead and state the parallelogram law that I've sort of illustrated with u and v before, but if I take u plus v, for example, or take v plus u, the resultant vector, I get a parallelogram here, and the resultant vector of adding those two vectors together. In other words, I can always make a parallelogram out of two vectors. The resultant vector, the vector I get when I add them together, is going to be the diagonal of that. So here is the vector u plus v, or v plus u, if you like. So that's called the parallelogram law. All right, on to our next operation, which is going to be scalar multiplication. All right, so when we talk about scalars, we're talking about a real number, essentially. Generally, we could have vector fields over scalars besides the real numbers, but whenever we talk about scalars, we're talking about real numbers, and we're normally going to let the letter C represent a scalar or any real number. And let's go ahead and let V, there's that notation, so we know we're talking about a vector there, be some vector. And let's go ahead and make my vector here. There it is. It's got direction and length, direction and magnitude. Okay, then we can find the vector C times V. And here's how we do it. It's going to be a new vector, and it's going to be a new vector with magnitude being, or length, with length being the length or magnitude. So I've been saying length, magnitude and length are going to be interchangeable. We talk about vectors. The length or magnitude of v times the absolute value of our scalar. Okay. Now, what's the direction going to be? The direction of this new vector will be the same if our scalar is positive. And of course, the direction will be the opposite of the original vector's direction if C is negative. Of course, if C is equal to 0, that just makes it the 0 vector. Alright, so a couple of examples here then. Let's take that vector that we just talked about, V, and let's make another vector u. Let's say this is the vector u right here, and let's suppose I wanted to find then maybe 2 times v. Alright, easy enough. I take a copy of v and another copy of v, and there it is. So it's this vector here that is 2v. Suppose I wanted to find the vector, how about negative 3u? Alright, so I'm going to send u in the opposite direction negative 3 times because of that negative. So here's a negative u, negative u, negative u, put them all together, and I get this vector here, which is negative 3u. Here's another one. How about 1/2 v? We can certainly multiply by a scalar that's less than 1, so I'm just going to take, I'll just do it here in same direction as the original vector v, just half as long. Alright, and maybe we could do something really crazy like this. How about 2u minus v? The way we think about that, so I'm sort of introducing scalar subtraction on the fly, really it's just addition. We can think of it as addition with a negative vector. That's the way we can think of subtraction. So 2u plus a negative v. So remember how we add. Let's start with 2u. We'll do that here in, let's see. Yeah, that's fine. So 2u, so I'm going to go 2u u, and that's not really that close, is it? Let's try that again. Here's u right here. Let me take the same color. There's 1u, there's 2u's. I'm going to add to that a negative v. Now v goes this way, so I'm going to have to send that in the opposite direction. So here is negative v. And now we're going to have 2u minus v. It's going to be this vector right here. That's 2u minus v, or 2u plus a negative v. Okay. And so again, that brings up this idea of subtraction of vectors. And we think of it simply as adding the negatives. So let's suppose I have a vector A that looks like this and a vector B that is equal to this vector. And let's suppose I want to find A minus B. Find A minus B. So I'm going to think about that as A plus a negative B. And so I'll start with A. Tack on a negative B. I'm going to have to move my A down a little bit. So I have room for my negative b. There's a. Negative b, so b in the opposite direction comes up this way. And then, of course, a plus negative b is this vector right here, or a minus b. There is what's called the triangle law when you're subtracting vectors. Notice that I could have just done this. If I want to take a minus b, I can take a and start a and b in the same spot. So start a there. Start b here, and then a minus b is going to be the vector that starts at the end of b and ends at the end of a. There's a minus b. Notice it has the same direction and magnitude as the way we found it originally.